Hi, welcome to series of webinars on optical network technologies and protocols. This is your friend Brahmanand in the journey of learning. As part of discussions on fiber optics, today's topic of discussion is basics of optical transmission, concepts on optical transmission and optical link devices. The basic transmission principle of fiber optics is the transmission between a transmitter and a receiver over optical fiber. The media of transmission is optical fiber, wherein my data is transported as light. The transmission link basically involves the transmitter which will have an electrical interface, the data encoder, modulator, the light emitter, and similarly light detector, data decoder, and the electrical interface and receiver. Both are connected by optical fiber. The transmitter will take data, could be an audio or video or any kind of data, and data gets encoded, modulated, and light emitting device emit the data as light to transmission media, which is optical fiber. If my data is analog in nature, as we discussed in one of our webinar, time division multiplexing is used to convert my analog data to a digital data as shown in this diagram, and optical transmitter will transport that digital data through optical media, and the reverse process takes place in my receiver, wherein the digital data will get converted to analog. The digital data is transported in the optical fiber based on the emitting device functions. Laser emits light into optical fiber whenever there is a digital 1. So during this time the light is present. So when a digital 1 is received by a modulator, the laser transmits the light. So the presence of light is indicative of a digital 1. Similarly, when I need to transmit 0, then the laser device goes off. It means that light is absent. And similarly, when digital 1 is received, it transmits the laser. So the precision of laser diode, the characteristics of laser diode is very important, because it has to transmit the light within a very less time period, and the accuracy of its switching from transmission to non-transmission based on digital 1s and 0s is very key in any optical transmission. Optical media, which is an optical fiber, as is made up of glass, which is made up of pure silica. The fundamental windows or wavelength windows wherein my attenuation losses are less are represented in 1850, 1310, 1550 and 1625 wavelength ranges. My laser will have a specification on the wavelength it is emitting. So it has to transmit the light based on a particular wavelength. So the specification of the laser is very important when we design our optical network. The launching power depends on the class of the laser, which we will discuss in a separate slide. But the launching power is represented either in dBm or in milliwatts. Normally, the launching power is represented in dBm for simplification. Assume my transmitter power is equal to say 100 milliwatts, then dBm is represented as 10 times the logarithm 10 of power in milliwatts divided by 1 milliwatt. If my power in milliwatt is 100 milliwatts, then logarithmic 10 of 100 give rise to 2. So log 10 of 100 is equal to 2. So my dBm is equal to 20 dB corresponding to milliwatt of 100. Because in optical transmission we always talk in terms of milliwatts, micro and nanowatts, it is very difficult to represent it in a microscopic milliwatts or microwatts. Instead, it is very useful if we represent it in terms of dBm. There are different kinds of lasers based on the risks involved with them, based on the power they emit. If a laser diode emits between 100 milliwatts to 1000 milliwatts, it is called as class 4. And the ability of the laser diode transmitting the output power depends also on the wavelength it is operating. So for a given wavelength, it operates in a range of output power. Say for example, for a class 2 laser which can operate from 415 to 750 nanometer, its power varies based on the lambda, based on the wavelength. So this is the representation of a class of lasers based on the risk associated with them, and because the class 2 laser, as it emits high power, it is very important that we don't see through the laser when it is emitting power. The class 1 laser can also work on different wavelengths, and its output power varies depending on the wavelength. So this is a representation in dBm. Say, for example, class 3B and 4 lasers, if they work on 1550 nanometer, their output power is 27 dBm, which is equivalent to 500 milliwatts. Suppose if there is an optical fiber cut between a transmitter and a receiver, or a network element 1 and network element 2, if there is a fiber cut here, it will rise a loss of signal at this particular network element, which will send an automatic laser shutdown command to its transmitter, and which will shut down its output, such that the transmitter 1 will get a loss of signal. So eventually an automatic laser shutdown commands moves from from receiver of network element 1 to transmitter of network element 1, which will also close its laser such that it will not emit any light to its transmission link, so that if an operator is working on this particular any, then there would not be any risk if he observes the laser directly from his eyes. So I mean, this is one of the advantageous factor of automatic laser shutdown when we are using lasers in our optical network elements. The receiver will do the exactly opposite of what the transmitter does. Firstly, the light is received by light detectors. The light detectors could be pin diodes or avalanche photodiodes, which are made of silica, germanium, and other elements. And once they are detected, they convert optical signal to electrical signals, and the decoders and demodulators will decode the signal and demodulate it, which gets converted to electrical digital data by the electrical interfaces linked to my decoder demodulator, and eventually my data reaches the end user. The light detectors, as we discussed, it could be pin photodiode or avalanche photodiode, wherein once my light is received by my photodiodes, it converts into electrical current by a principle of wherein it gives rise to holes which moves towards the anode and electron which moves towards the cathode, creating electrical charge, current. So we will discuss about light detecting photodiodes, avalanche photodiodes in a separate session. But this session, it is not to discuss about the principle of these diodes, but to understand what is the importance of minimum power and maximum power with reference to these receivers or diodes. If my power received by my receiver is less than the minimum power required, then it cannot analyze the data. It cannot convert the optical signal to electrical signal. So it should be my power received by my photodiode should be in a band. If the power is less than the minimum power required by the photodiode, then that is called as the receiver sensitivity. So it should be, the power should be more than the receiver sensitivity. If the power received by the photodiode is more than the saturation power, then photodiodes would be damaged. So an operator, or as part of a network design, will have to ensure that the power received by the receiver will be within the band between saturation and sensitivity for photodiodes to work efficiently. Basically, all the interfaces which are used in the optical transmission link are classified based on the optical network applications it's being used, and digital signal bit rate for which my transmitting and receiving devices are used, and the wavelength range for on which these transmitting and receiving devices work. So these three parameters are very important to classify my optical devices. This is based on G957, wherein my classification is done based on the optical interfaces and the application that are being used. Say, for example, if I have a source which works on short haul represents approximately 15 kilometers, and if it uses the optical fiber which is based on G652, then it is called as S-1.1. S indicates short haul, 1 indicates STM level, and 1 indicate 1310, the wavelength on which it works. Similarly, S12 indicates short haul STM1 and 1550. Similarly, L1.1 indicates long haul, which can be 40 kilometers, or it can be for a long haul of 80 kilometers. 1 indicates STM1, and the second one indicates the wavelength on which it is working. Similarly, say for example, L4.3 means it's a long haul, STM4. 3 indicates it is using G653 type of fiber. So my laser, if it comes specification is used, my laser specification is used as L-4.3, it means that my laser can be used for long haul, it can be used for STM4, it can be used with G653 cable, and within 1550 nanometer range. One of the most important parameter that we need to give importance while planning for an optical transmission link is the launching power of my laser. For example, if my laser is used for S1.1, then it has to be in the range of minus 8 dBm to minus 15 dBm. S1.1, as we discussed, means that it is for short haul STM1 and which is using 1310 nanometer. And similarly, say for example, if it is L1.1, it should my output power should vary from 0 dBm to minus 5 dBm. If it is used for the same wavelength of 1310, the long haul STM1 and 1310, then as can be seen from this diagram, the power has to be in the range from 0 dBm to minus 5 dBm. One more parameter that we need to give importance is receiver sensitivity. So if my receiver, whatever could be the diodes we use at the receiver, it has to be abiding the standard mentioned in G957, which indicates that if it is used for short haul with for STM1 and at 1310 nanometer, then its receiver sensitivity should be minus 28 dBm and overload is minus 8 dBm. It means that if my received power is more than minus 8 dBm, then it will get saturated and there will be more chances that my photodiode might get damaged. So when planning an optical network, we'll have to give importance to many parameters, but these two parameters are of high importance. Optical fiber is the media for communication between my optical transmitter and receiver. This is a typical representation of my optical fiber, which will have core, cladding, a buffer and the jocket. Core is the most central part of my optical fiber, whose refractive index is less than cladding. So refractive index of core is less than refractive index of cladding, and the buffer and the jockets are put in on the optical fiber to safeguard it. Optical fiber works on the principle of total internal reflection. Whenever I want to transmit my light with the data in optical fiber, laser will have to transmit this particular light within the critical cone so that the light is emitted to optical fiber such that the angle of incidence into core is more than the critical angle of incidence. If the angle of incidence is reduced, then my light will get refracted to clouding. It means that my signal will get lost. The refractive index of core is less than refractive index of cladding, so that because of the change in the refractive index, my light will get reflected back. But the angle of incidence has to be such that it should be greater than the critical angle for the light to reflect back. So once my light touches the interface between the core and the cladding, it reflects and passes with the total reflection further. As you can see, light will have multiple angle of incidence. Some percentage of my light might get refracted to my cladding, which will gives rise to attenuation. But the percentage of my refraction should be managed such that high percentage of my light goes within my core. There are different kinds of optical fibers, namely multimode and single mode. Multimode fiber will have more core diameter compared to my core diameter of a single mode fiber. The basic difference is in the diameter of them, and one more difference is my multimode fiber as it will have more modes, it can take more power within the core, because the area for the light to transport would be more, so it can take more data, as the modes of transmission would also be more. But because it will have more diameter, the possibility of the light guiding through it would be less compared to my single mode fiber. That is the reason why single mode fibers are used for long distance communication, whereas multimode fibers are used for short haul communication. So my objective of this webinar was not to discuss in a detailed way about optical fiber, which we can discuss in a separate session, but the objective was to discuss in high level the optical devices or the optical components in my optical transmission link. Thanks for watching.